For 37 years, the entire human picture of the seventh planet rested on a single afternoon of photographs. On the 24th of January 1986, Voyager 2 swept past Uranus, took its pictures, and continued on into the dark. What came back was almost nothing. A pale blue-green sphere. No bands, no storms, no visible weather. For nearly 4 decades, that single bland portrait was the whole story. An entire generation of astronomers came up, did their work, and retired, knowing the planet only by that one quiet image. Then a sharper eye finally turned its gaze in a kind of light our own eyes cannot see, and the calm marble vanished. What stared back was something else entirely. So how does an entire world stay hidden in plain sight for 37 years, 2 billion miles from home, and what does it mean when the disguise finally falls? Get comfortable, subscribe if you have not, and stick around, because the path we're about to follow into the seventh planet goes somewhere most space documentaries never quite reach. Let's get into it. Part 1. The Pale Marble. There is a photograph of Uranus taken on the 24th of January 1986 that did something almost no other photograph in the history of astronomy has managed. It held a planet still, not in the sky, in the human imagination. For 37 years, that single image, a pale, soft blue-green sphere, almost perfectly smooth, almost perfectly empty, was the whole picture we carried of the seventh planet from our sun. An entire generation grew up, became scientists, taught their own students, and retired, all the while believing they knew what Uranus looked like, because they had seen the picture. Almost everyone who looked at it agreed on a single word, and that word was boring. We were wrong, not in a small way, not by the kind of margin that gets corrected in a footnote in the next edition of the textbook. Wrong in a way that took a different telescope and a different kind of light to even begin to see, and wrong about a planet that had been quietly waiting for almost 4 decades, sitting in the dark at the edge of our solar system, hiding more strangeness than anything else humans have looked at and ignored. I want to take you out there tonight, slowly, carefully, with patience, the way the planet itself requires. Because what the James Webb Space Telescope finally saw when it turned its eye on Uranus a few years ago is one of the strangest stories our solar system has produced, and almost none of it has reached the general public yet. The polar cap nobody noticed before. The hidden moon Voyager missed. The vortex turning above the spin pole. The cliff so tall on one of the moons that you could fall off it for 10 minutes before hitting the bottom. The diamond rain falling through a frozen ocean underneath the clouds. The magnetic field knocked so far off its axis that it tumbles instead of pointing. The sideways rings, the single ancient impact that explains all of it, and hiding underneath everything, the quiet possibility that this wounded, sideways, frozen, hostile world we have all but ignored may be the closest local example of the most common kind of planet anywhere in the galaxy. Tonight we're going to pull the disguise off Uranus, not all at once, the way it actually happened, the way it actually rewards us when we do. It is worth saying out loud before we begin what the disguise was. The disguise was a single set of photographs taken across a short window in late January 1986 by a spacecraft moving so fast it had barely 6 hours of close encounter time and would never come anywhere near Uranus again. Those photographs showed almost nothing. No bands, no spots, no storms, no visible weather. The atmosphere appeared serene. The disk looked, to anyone glancing at the image, like a plain blue-green marble suspended in black. Compared to Jupiter's churning belts, compared to Saturn's geometric rings, compared even to little Mars with its dust storms and ice caps, Uranus seemed quiet, empty, featureless. The world of the late 1980s was already busy with other space stories. Halley's Comet was returning that year. The Challenger had broken apart 8 days before the Uranus flyby. And Uranus, the apparent flat marble, slipped out of the conversation almost before the conversation began. This is the thing about a planet hiding behind a disguise. It does not have to actively conceal anything. It only has to stand still long enough for someone with a small telescope to take a single quiet picture, and then trust the silence afterward. 1986 was that picture. 1987 through 2023 was the silence. In those decades, almost no one looked closely. There were exceptions. The Keck telescope in Hawaii, working in near-infrared with adaptive optics that corrected for the shimmer of our atmosphere, occasionally caught bright spots on Uranus that visible light hid completely. The Hubble Space Telescope took a careful Uranus image now and then, the kind of thing that would appear briefly in an astronomy magazine and then be filed away. A few ground-based campaigns, often led by the same handful of patient observers, charted the planet's slow weather across seasons that stretch beyond a working career. But for the general public, and even for most astronomers who did not specialize in the outer solar system, Uranus was still the photograph from the flyby, the blue marble, the boring one, the planet nobody wanted to visit. It turns out the planet was never calm. It was only photographed in the wrong light. It was only photographed during a hemisphere's quiet season. It was photographed by a camera that did not see infrared, and so could not see most of the weather that was actually happening. The serenity in that single most famous picture of Uranus is not the planet's serenity. It is our limitation, projected onto its face. When you understand that, the dismissive shrug that the world gave Uranus for almost 4 decades starts to feel less like good judgment and more like a kind of accident. We did not look closely. We looked once, briefly, in the wrong way, and then assumed we knew. The patient lesson the planet has spent the last few years giving us, through the eye of a much better instrument, is that this is exactly the kind of mistake that is easy to make and very, very expensive when you make it about an entire world. Because the same lesson generalizes. There are other places, moons, asteroids, distant exoplanets, that we have looked at once and decided we knew. There are corners of the universe right now that may be sitting under exactly the same kind of disguise, waiting to be looked at properly, waiting to be seen by an instrument we have not yet built. Uranus, in other words, is going to teach us something about ourselves before we finish learning about it. But to understand what is hiding behind the disguise, you have to know how the planet got there in the first place. You have to know how it was found. You have to know the strange small story of a musician with a homemade telescope in a backyard in England, and a comet that turned out not to be a comet, and the first world ever added to the human map of the sky by an instrument rather than the naked eye. Because Uranus has only ever given up its secrets when forced. It has been that way from the very first night anyone noticed it was there. Part 2. Discovered. Already hiding. The man who found Uranus was not, at the moment of discovery, an astronomer. He was a musician. His name was William Herschel, and in 1781, on the 13th of March, he was standing in the cool spring air at the back of a small house in Bath, England, sweeping the southern sky with a telescope he had built himself. He was 42 years old. He had been born in Hanover, then in northern Germany, into a family of musicians, and had come to England a couple of decades earlier to make a quiet living as an oboist, an organist, and a composer of symphonies that the world has now almost entirely forgotten. The telescope was a hobby. The hobby had grown serious. By that spring he had already built several reflectors, instruments that used polished metal mirrors instead of lenses, because metal mirrors of sufficient quality were easier for a self-taught craftsman to produce in the dark of his own basement than the precisely ground glass lenses fashionable astronomers preferred. The telescope he used that night was about 7 feet long. It looked, by modern standards, almost charmingly modest. Standing next to it, peering into its eyepiece in the chilly Bath garden, was, in a way that he could not yet have imagined, the man about to add a planet to the universe. He was sweeping a region of the sky in the constellation Taurus, a careful, methodical, almost tedious operation, scanning small section after small section, noting down everything he saw. The point of the work was not to find anything in particular. It was to make a thorough census, a kind of personal catalogue of every faint object visible in his garden. Most of what he saw was stars, exactly where stars were supposed to be. Stars are points. They twinkle at the edge of perception. They look the same through a small telescope as they do through a giant one. Small, sharp, unmoving. And then he found one that was not a point. He noticed it because, through his eyepiece, it did not behave like the rest. It had a small disk. It looked, to the trained eye of someone who had spent thousands of nights looking at stars, very slightly fuzzy. Stars are not fuzzy. Stars are immaculate pinpoints. This object had a small visible size. He looked again the next night, and the next, and he saw it had moved against the background stars. Not the kind of motion you can see in a single observation, but the kind that becomes obvious if you compare careful sketches across nights. Stars do not move. Comets do. He concluded reasonably that he had found a comet and wrote it up under that name. He sent his observations to the Royal Society in London. He waited to see what professional astronomers would make of his discovery. What happened next is the small turn that gives this story its particular shape. The professionals examined his observations. They tried to fit a comet's orbit to the new object. They could not. A comet, by definition, moves on a highly elongated path that swings close to the Sun and then back out, and the math for such an orbit has a specific signature in the way an object's position changes across nights. The object Herschel had found did not move that way. It moved on a path that looked, the more they checked, almost perfectly circular. It was very far away. It had a measurable size. Its movement matched the motion you would expect from a planet on a wide, slow, distant orbit beyond Saturn, in a region of the solar system nobody had thought to look for one. The Royal Society slowly came to the conclusion Herschel himself had not quite reached. He had not found a comet. He had found a world. This had not happened before. Mercury, Venus, Mars, Jupiter, Saturn. Every planet known to ancient and medieval people was a naked-eye object. They had been there in the night sky for as long as anyone had been looking up. Children in Babylon, in ancient Greece, in Tang Dynasty China, had all known the same 5 wanderers. There had been, in the entire recorded history of human astronomy, exactly 5 planets. And now there were 6. The first planet ever added by the use of a telescope. The first planet that had simply been too dim and too far and too quiet for anyone to notice for thousands of years without help. The first planet you had to go looking for. This is the small detail that becomes the theme of the entire Uranus story. From the very first moment we knew it was there, Uranus had only revealed itself when we did something more than just look up. We had to build something. We had to sweep the sky carefully. We had to compare nights. We had to trust the small disk against the stars, and the small motion across the background, and the work of the professionals down in London who finally pinned down its orbit. Uranus has never been an obvious world. It has always been the world that rewards patience and the willingness to look closer. It also has always been a planet a little out of step with the others. Herschel, when he realised what he had, suggested naming the new world after King George III, who was about to become his patron. The Georgian star, Georgium Sidus in Latin. For decades afterwards, depending on which country's books you read, the new planet was called the Georgian, or simply Herschel, or finally after much wrangling in continental Europe, settled on a name that fit the older Greek and Roman convention. Uranus, the father of Saturn, the sky god above the planet of time, the 7th world from the sun, the first found with a telescope named for the oldest figure in the lineage of the gods. Herschel did very well by it. He was made the king's astronomer. He moved to a larger house in Datchet, then later to Slough near Windsor. His sister Caroline became one of the most accomplished observational astronomers of the era in her own right. The telescopes the Herschels built kept getting larger. Eventually William built a 40-foot-long reflector that was, for some years, the largest telescope in the world. He spent the rest of his life cataloguing nebulae and double stars and the structure of the Milky Way galaxy. By the time he died in 1822, the planet he had found was a routine feature in any astronomy textbook. The shock had worn off. Uranus had become part of the standard sky. The first planet found with a telescope had been quietly absorbed into the family of worlds we already knew, and the next century would mostly let it sit there, patient, distant, quiet, until somebody else came along with a better instrument and a better question. The next somebody else, when they finally came, would not be a single musician with a backyard reflector. They would be a small refrigerator-sized spacecraft, hurled by chemical rocket out of low Earth orbit nearly 2 centuries later, and they would not stay in our garden for years. They would be in front of Uranus properly for about 6 hours. Part 3, January 24th, 1986. On the 24th of January 1986, a spacecraft about the size of a small car came within roughly 81,500 kilometers of the cloud tops of Uranus. The number translates to about 50,600 miles, close enough that, if Uranus had a solid surface and a habitable atmosphere, you could have looked up and seen the spacecraft pass overhead as a slow, bright dot. Were you somehow standing on it? It did not, and you would not have been. But the geometry is what matters. For about 6 hours of close encounter science, a single instrument package, built by people who had never seen a real photograph of the planet in their lives, was right next to a world humans had been guessing about for 205 years. The spacecraft was Voyager 2. It had launched in August of 1977 from Cape Canaveral on a Titan Centaur rocket. By the time it reached Uranus, it had already, in the previous 9 years, flown past Jupiter and Saturn, returning images that rewrote the textbooks for both. It had then begun the long, slow coast outward, gathering speed in a way only the gravity of giant planets could provide on a trajectory chosen specifically because of the rare alignment of the outer planets in the late 1970s and the 1980s, a window that would not open again for nearly 2 centuries. If the launch had been delayed a couple of years, Voyager 2 could not have reached Uranus on a single mission. The geometry of the outer solar system itself would have closed the door. As it was, the spacecraft arrived right on schedule, and across that single afternoon it became the only object ever built by human hands to come close to Uranus, and remains so today, 4 decades later. It is worth pausing to feel the shape of that fact. We have sent rovers to Mars that have, between them, accumulated more than 50 years of operational time on the Martian surface. We have flown probes through the rings of Saturn for over a decade. We have parked spacecraft in orbit around Mercury. We have crashed a probe deliberately into the south pole of the Moon. We have 100 different missions, past and present, to almost every interesting body in the inner solar system. Voyager 2's close encounter with Uranus has been our entire close-up acquaintance with the planet, and it lasted in total useful time about as long as a transatlantic flight from London to New York. In those 6 hours, Voyager did extraordinary work. Its cameras turned, its plasma instruments listened, its radio waves bent through the Uranian rings and the upper atmosphere on the way back to Earth, carrying with them the chemistry and temperature of the layers they had passed through. Voyager's imaging team confirmed the existence of 10 previously unknown rings, narrow dark threads around the planet that had been hinted at 8 years earlier by an experiment in which astronomers had watched a star blink behind Uranus and noticed the star flickered before and after the planet itself moved across it, as if the planet had been wearing a veil. Voyager confirmed the veil. It also discovered 10 new moons, lifting the count from the 5 previously known major moons to 15. The additional ones small, dark and tucked in close to the rings. It returned the first close photographs of Miranda, the smallest of the major moons, and revealed a tortured, fractured surface that nobody had expected. Cliffs, grooves, broken ridges, including the tallest known cliff face in the solar system, which we will come back to later in this video. It measured a magnetic field whose strangeness, when its numbers finally settled, would keep theorists arguing for years. But the photographs are what the public got, and the photographs are what froze the story. The visible light cameras on Voyager 2 returned images of Uranus that showed almost nothing. No belts, no spots, no storms, no bands, no visible cloud structures, just a pale, soft blue-green sphere with a barely perceptible hint of darker shading toward one pole. Compared to Voyager's earlier images of Jupiter, with its hurricane bigger than Earth that has been turning for centuries, and Saturn, with its golden bands and its impossible delicate rings, Uranus looked almost embarrassingly plain. The cameras were doing exactly what they were built to do. They were photographing exactly what was actually in front of them. The problem was that, in visible light, Uranus genuinely is, at the wavelengths a human eye can see, a faintly banded blue-green sphere without obvious weather. The methane in its upper atmosphere absorbs red wavelengths and reflects blue-green. The cloud deck visible in those bands is far above any storm activity, and the planet was being photographed during a particular season, with one entire hemisphere tipped almost directly toward the sun and the other entirely away, in a configuration we'll get to soon that makes the visible disk particularly quiet. The mission scientists understood at the time that their cameras were limited. They wrote about it in their papers. They noted the absence of obvious features. They explained that infrared and ultraviolet imaging in future missions would almost certainly find structures the visible cameras had missed. But future missions were a long time away, and the cultural image of Uranus, the picture that ended up in textbooks and on lunchboxes and in space documentaries for the next 4 decades, was the visible light one, the blue marble, the empty sphere. There is a particular sadness to the timing of the Voyager 2 encounter. 8 days before the spacecraft's closest approach to Uranus, on the 28th of January 1986, the Space Shuttle Challenger had broken apart 73 seconds into flight, killing all 7 of its crew. The cultural attention of the United States and most of the watching world was on the shuttle program, on the inquiry that would follow, on the larger question of what would happen to crewed spaceflight in the aftermath. Halley's Comet was visible in the morning sky. The Cold War was still going. The Iran-Contra hearings were a year away. Uranus, by comparison, was a quiet headline at the bottom of the science section. The flyby came and went. The images were released, looked at, and gradually slid out of the news cycle, and most of the world moved on. The instruments themselves did not stop returning data. Voyager 2 continued past Uranus and on toward Neptune, which it reached in 1989, the last of the great planetary encounters of the original Voyager mission. After Neptune, Voyager 2 turned downward out of the solar plane and began the long, slow voyage into interstellar space, where it remains today, gradually drifting toward an empty patch of sky in the constellation Sagittarius. It will continue to coast for the rest of human history, and almost certainly long beyond. It will outlive the people who built it. It will outlive every civilization that knows its name. It will eventually, in some unimaginable far future epoch, pass close to another star. It will never again come close to Uranus, nor, since then, has anything else. We sent it past once. The window of opportunity closed behind it. The afternoon of January 24th, 1986 was the entire physical visit. 6 hours. 6 hours, and a single set of bland blue photographs became the only intimate look humans have ever gotten at the 7th planet from the Sun. That, more than anything else, is the shape of the gap that the James Webb Space Telescope finally walked into, almost 4 decades later. There is a 37-year silence between when our last spacecraft left and our best telescope finally turned its eye on what we'd ignored. To appreciate what Webb did, you have to first appreciate what those 37 years felt like for the small handful of astronomers who never quite let Uranus go. Part 4. 37 Years of Quiet. For most of the 37 years between Voyager 2 and the James Webb Space Telescope, what we knew about Uranus was, in the public mind, frozen at the level of that one set of photographs. In the private work of a small community of planetary scientists, however, the picture was changing slowly. Not because new spacecraft were arriving, none did, but because telescopes on the ground and the Hubble Space Telescope in low Earth orbit kept improving in ways that very slowly chipped at the dead photo narrative. The most important of those telescopes was Keck, on the summit of Mauna Kea on the Big Island of Hawaii. Keck is two 10-metre mirrors sitting at about 4,200 metres of altitude, above almost half of the Earth's atmosphere. It has, since the late 1990s, used a technology called adaptive optics, which corrects in real time for the shimmer that turbulent air would otherwise add to its images. With adaptive optics on, a large telescope on the ground can produce images that approach the sharpness of a telescope in space. Aimed at Uranus in near-infrared light rather than visible light, Keck began returning images that did not look like Voyager's bland blue marble at all. In Keck's infrared images, the disk of Uranus had structure. There were bright spots that came and went. There were bands. There were what looked like storm features. Patrick Hamill and Imke de Peter and Larry Sromovsky, and the small group of planetary scientists who specialized in the outer solar system, began publishing papers year by year that very gradually undid the dead photo myth. They tracked individual storm features for weeks at a time. They watched the planet's cloud activity rise and fall in a pattern that, when you laid the years end to end, started to look like seasons. Slow Uranian seasons, each lasting around 21 Earth years. That meant the activity Voyager had photographed in 1986 had simply been the quiet half of a much longer rhythm. Voyager had visited in a calm time. Of course it had seen a calm planet. If you visit a Caribbean beach in February, you do not see hurricanes. That does not mean hurricanes are not a feature of the place. The Hubble Space Telescope in low Earth orbit contributed its own quiet sequence of Uranus images. Hubble, with its sharper resolution than ground-based telescopes had managed in optical wavelengths, caught features Voyager had missed. It eventually imaged the planet's outermost rings, two faint dusty ones that had not been confirmed by Voyager at all, by simply staring at Uranus long enough that the diffuse material around the planet became visible against the background. The first of those two dusty rings was published in 2003. The second followed in 2005. The ring system that for almost 20 years had been thought to have 11 rings, after Voyager added 2 to the 9 that had been discovered by stellar occultation in 1977, was quietly bumped to 13. That is the number that stands today. There were also Hubble auroral campaigns. Aurorae are produced when charged particles from the sun stream along a planet's magnetic field lines and slam into the upper atmosphere, exciting atoms and molecules to glow. On Earth, this happens in tidy rings around the magnetic poles, which more or less line up with the rotational poles, and the result is the visible auroras of high latitudes. On Uranus, the picture is much weirder. The magnetic field is tilted at 58.6 degrees from the rotation axis. We will spend a whole part of this video on that strange field a little later. For now, what matters is that the aurorae, as they appear on Uranus, do not fall at the spin poles, the way they do on Earth. They fall where the magnetic axis hits the upper atmosphere, which, depending on which moment in the planet's 17-hour rotation you catch them, can be almost anywhere on the disk, including very close to the equator. Hubble imaged Uranian aurorae in 2011 and again in 2013 and 2014. The images, when they were finally published by a team led by the French planetary scientist Laurent Lamy, were both faint and bizarre. The aurorae were small. They wandered. They sometimes appeared as patches rather than rings. They did not look like anything Earth had ever produced. They were one more line in the slow accumulating evidence that Uranus was a much stranger world than the Voyager photograph had ever managed to convey. The biggest single contribution from the ground in those years arrived in 2018, in a paper led by Patrick Irwin of the University of Oxford, using the Gemini North 8.1 metre telescope on Mauna Kea, also in Hawaii, and an instrument called the Near Infrared Integral Field Spectrometer, or NIFS for short. NIFS does not just take pictures, It takes pictures and a full spectrum of the light at every pixel of the picture, so that you can ask what wavelengths of light are being absorbed at every spot on the planet's disk. Irwin's team aimed NIFs at Uranus and looked at the absorption signatures in the upper cloud deck. What they found settled a question that had been open for decades. Uranus's clouds, the team reported, are dominated by hydrogen sulfide ice. Hydrogen sulfide is the gas that gives rotten eggs their smell. It is the compound that hangs around marshes and decomposing organic matter and the inside of sewage systems. It is the gas a chemistry teacher will use, very gingerly, to teach you the difference between unpleasant and dangerous. And it is the gas that, when frozen into ice particles at the cold of Uranus's upper atmosphere, forms the bulk of the cloud deck we can see from outside. Irwin himself, in the press release that accompanied the paper, had one of the more memorable scientist quotes of the decade. "An unfortunate human descending through Uranus's clouds," he said, "would be met with very unpleasant and odoriferous conditions. Translated out of polite scientific phrasing, it would smell overwhelmingly of rot. Not metaphorically, not in a clever literary sense, literally. The first thing you would register, if you could somehow survive the cold and the pressure long enough to register anything, would be the overwhelming chemical announcement of decay. The whole planet, in a real sense, smells like a cracked egg left in the sun, at temperatures so far below freezing that the smell could never escape the cloud deck into anything warmer. It is also, importantly, a chemistry that distinguishes Uranus and Neptune from their bigger siblings. On Jupiter and Saturn, where the atmosphere is much warmer and the cloud structure is dominated by ammonia, hydrogen sulfide is locked away in deeper layers and never reaches the visible top. The clouds we see on Jupiter and Saturn are ammonia-rich, smelling by comparison like a household cleaner rather than a rotting egg. On Uranus and Neptune, the temperatures are so cold that ammonia condenses out at deeper levels, and the layer we see from outside is the one where hydrogen sulfide takes over. The chemistry tells you something about where in the solar system you are. The deeper into the cold you go, the less Jupiter your planet looks like, and the more Uranus. There was a slow accumulation of papers in those years on storm activity, on cloud feature lifetimes, on whether Uranus's quiet behaviour across the late 1980s and early 1990s was really seasonal or partly due to instrumental artefacts. There were arguments about how much heat the planet was leaking out of its interior, with a strong consensus emerging that the answer was almost none. Uranus radiates roughly 1.06 times as much energy as it receives from the Sun, which is essentially a number indistinguishable from radiative balance, while Neptune, our other ice giant, leaks more than 2.5 times the energy it receives. Uranus, in other words, has its furnace switched off, and Neptune does not, and nobody could explain why. The slow accumulation of papers was important, but for most of those 37 years the central image stayed the same. The blue marble, the empty disk, the planet nobody wanted to visit. There is a quiet weight to that 37-year gap. An entire generation of planetary scientists came up, did their work, retired, knowing the 7th planet of our own solar system almost entirely by one short visit and a small handful of careful ground-based campaigns. Some of them died. Some of them are alive to see what Webb finally pulled out of the fog. The science of the last few years has been beautiful, but the sentence underneath the beauty, the sentence that has nothing to do with technology and everything to do with us, is much simpler. We waited a long time before we looked closely. The world rewarded the patience. The disguise came off when somebody finally pulled. Part 5. The Eye That Saw in a Different Light. On Christmas Day of 2021, an Ariane 5 rocket lifted off from a launch pad near Kourou, in French Guiana. The payload was a folded 6.5-metre telescope made of 18 hexagonal beryllium mirrors coated in a thin layer of gold. It carried 4 instruments. It carried a tennis court-sized sun shield made of 5 layers of aluminum-coated polyimide film. It had been designed, redesigned, delayed, debated, defunded, refunded, and finally built and flown over the course of more than 2 decades of engineering effort, at a final cost a little above $10 billion. It was the most expensive, most complex, most powerful space telescope ever launched. It was the James Webb Space Telescope, and after the launch and the long, delicate cruise out to a stable position roughly 1.5 million kilometers from Earth, and after the careful unfolding of its mirror and its sun shield, and after the long, quiet cooling down of its detectors to the temperatures necessary for infrared observation, it opened its first eye. In June of 2022, it began its first science operations. By the spring of 2023, it had been busy for nearly a year imaging galaxies in the early universe, atmospheres of exoplanets, the surfaces of asteroids, the interiors of dust clouds where stars are being born, and then, on the 6th of April, 2023, NASA released the first Webb image of Uranus. I want to put you, for a moment, on the morning that image came down. Imagine a control room in Baltimore, or in Pasadena, or in Greenbelt, Maryland, where the team has stayed up late watching the data arrive. The first frames come through as bands of numbers, then as raw exposures, then as registered, calibrated, stretched composites. Somebody adjusts the color mapping. Webb sees in infrared, in wavelengths that human eyes cannot, and so the data has to be assigned colors a human can interpret. The first stretched composite resolves on a screen. A face turns toward it, then another, then everybody. The blue marble of 1986 is gone. In its place there is a planet with structure. There is a vast bright cap sitting over the north pole of Uranus, a hood of pale haze that simply was not visible in the Voyager photographs and was only ever hinted at in Hubble and Keck imagery. The cap is huge. It covers a sizable fraction of the disk. It is bright. It has a slightly off-center point of even greater brightness inside it, a small luminous knot at the rough center of the cap. That knot, the imaging team will explain in the months that follow, is the polar vortex, a stratospheric cyclonic structure anchored above the planet's spin pole, warmer than the air around it, turning patiently, anchored by the rotation of the planet beneath it. Around the cap there are bright methane ice clouds, scattered storms that ride the edge where the cap thins out. There are visible bands of subtly different brightness. There is the sense of motion. There is, for the first time in human history, a real photograph of Uranus that looks like an active planet rather than a quiet one. And around the planet, finally, the rings. Most people have never even heard that Uranus has rings. They are nothing like Saturn's. Saturn's rings are bright, geometric, almost theatrically beautiful. The kind of feature that pulls the eye in any photograph of the planet. Uranus's rings are thin, dark, and very faint. They are made of material darker than charcoal, with an albedo around 3%, almost certainly composed of water ice contaminated by radiation-processed organic compounds that turn black over geological time. They are arranged in narrow threads, 13 named rings now, after Hubble added the 2 outermost ones 2 decades ago. Webb captured 11 of those 13 in a single image, including, very faintly but clearly, the Zeta ring. The Zeta ring is the closest ring to the planet, a diffuse dusty band that was barely sketched in by Voyager and only sporadically detected by Keck in the years afterward. Webb, in one shot, did what only one other telescope on Earth had managed to do, and made the Zeta ring real. The thing the photograph does not quite show, because all the geometry has to be inferred from context, is that the rings are not lying flat the way Saturn's do. Saturn's rings circle Saturn's equator, and Saturn's equator is tilted only 26 degrees from the plane of its orbit. So from any vantage point in the inner solar system, Saturn's rings look like a flat plate around a ball, sometimes tilted toward us, sometimes edge-on, but always close to horizontal. Uranus's equator is tilted 97.77 degrees, so its rings, which sit in the planet's equatorial plane, are tilted with it. They stand vertically. From any vantage point near Earth's orbit, the rings of Uranus look not like a flat plate, but like a target painted around the planet. Concentric circles, perpendicular to the line of sight, the planet sitting in the middle of them like a bullseye. Webb captured that orientation perfectly. The image is, if you let yourself sit with it for more than a glance, one of the most quietly strange things in all of solar system astronomy. A planet does not tip itself over. Something out there did this to it. The vertical rings are the fingerprints of whatever did. In December of 2023, NASA released an extended Webb composite that took the first image's surprises and ran them in higher resolution and across more wavelengths. The cap was clearer. The vortex was clearer. The storm clouds at the cap's edge were more numerous. 14 of the planet's then 27 moons appeared as small bright points around the planet, including all 5 of the major moons: Miranda, Ariel, Umbriel, Titania, and Oberon. The rings were sharper. The vortex's stratospheric warmth showed up at certain wavelengths and faded at others, a signature consistent with a polar cyclonic structure rather than a cloud feature, anchored to the rotation pole rather than drifting with the atmosphere. And then, in February of 2025, the campaign produced a finding that even most of the team had not expected. A planetary scientist named Mariam El-Mutamid and her colleagues, going carefully through Webb NIRCam images of the inner ring system, noticed a faint moving point near the ring belt that had not been catalogued. They tracked it across multiple exposures, separated by hours and days, and watched its position drift in a way consistent with a circular orbit at around 56,000 kilometers from the planet's center. Its brightness matched the small dark moons in that region. They announced the discovery in early 2025. The new moon was given the provisional designation S2025U1 and an estimated diameter of roughly 10 kilometers, about 6 miles across. It joined the inner moon population between 2 known small moons, Bianca and Ophelia, lifting Uranus's confirmed moon count to 28, and then, after follow-up resolution of other Webb candidates, to 29. The new moon had been there in 1986 when Voyager 2 flew past. It had been there in 1781 when Herschel first noticed Uranus. It had been there for almost certainly billions of years. But Voyager's cameras, at the close approach geometry that mission flew, could not resolve objects smaller than about 20 or 30 kilometers across in the ring zone. The new moon was simply below the threshold of the instrument that had been flying past it. It took the most powerful telescope ever built, looking from 1.5 million kilometers from Earth, which is to say, looking from the suburbs of Earth out into the deep dark of the outer solar system, to finally catch a moon that had been hiding next to its planet the whole time. The same instrument that exposed the planet's weather is still finding pieces of its family we did not know were there. That is what Webb did. That, in essence, is what makes the last few years of Uranus science different from the 4 decades before. We finally built an eye sharp enough to pull the disguise off. The disguise that fell, when Webb pulled, was never just about a planet looking calm in a single bad photograph. Underneath the disguise was a world more strange than nearly anything humans have studied in our own solar system. Now that we can finally see it, we can start to ask the deeper question. Not just what is hiding under the calm photograph, but why does Uranus hide everything it hides in the first place? Why is this world the way it is? And the answer, the more carefully we look, all comes back to the same single ancient incident at the dawn of the solar system. Something happened to Uranus. The next part is what happened, and how we know. Part 6. The Tilted World. To understand why Uranus is the way it is, you have to start with the most absurd single fact about it. It is lying down. Every other planet in our solar system rotates more or less upright, the way a top spins on a table. The axis of rotation points up and down, or close to up and down, while the planet circles the sun. There is some variation, of course. Earth's axis is tilted 23.44 degrees away from straight up. The tilt that gives us seasons, the tilt that puts winter in the northern hemisphere when the North Pole tips away from the sun, and summer when it tips toward. Mars is tilted about 25 degrees, very similar to Earth, which is part of why Mars has roughly recognizable seasonal patterns even with its much longer year. Jupiter is barely tilted at all, just over 3 degrees. Saturn is about 26 degrees. Neptune is about 28 degrees. The whole family of planets, with the exception of Venus, which is a weird case of its own, lives in a range from 0 to about 30 degrees of tilt. Not Uranus. Uranus is tilted 97.77 degrees. That is past 90. That means the planet is not just leaning, it is past vertical. Its north pole, instead of pointing up out of the orbital plane the way a normal planet's would, points slightly below the plane. The rotation axis lies almost in the orbital plane itself. The planet is not spinning, it is rolling. Imagine a bowling ball rolling down a lane instead of a top spinning on a table, and you have something close to the right picture. The planet rotates roughly perpendicular to the way most worlds rotate. This is not a small detail. This is not a minor anomaly that the textbook mentions in a footnote and then moves on from. This is the most extreme axial tilt in the entire solar system, by a margin that is not even close. The next most tilted planet, Saturn, is at 26 degrees. Uranus is at 97. Uranus is more than 70 degrees past the second-place finisher. There is, in the catalogue of solar system planets, Uranus, and there is everybody else, and the gap between them is enormous, and the consequences ripple through everything. The first consequence is the most obvious. Because Uranus lies on its side, its poles do not point sideways the way Earth's do. They point toward the orbital plane, which means, as the planet circles the Sun across its 84 Earth-year orbital period, the pointing of the poles changes dramatically. For roughly 21 Earth years, one pole is aimed nearly straight at the Sun. We will come back to what that means in detail in the next part. For roughly 21 years after that, the planet has passed through equinox and is in a configuration where, briefly, both hemispheres get something like a day-night cycle, though stretched and odd. Then, for the next 21 years, the opposite pole takes its turn, then equinox again. The cycle takes the full 84 years to complete. We are right now, in the mid-2020s, approaching the planet's next northern summer solstice, in late 2028, the moment the North Pole points most directly at the Sun. The polar cap Webb has been imaging is brightening as that moment approaches, and Webb is watching it brighten season by season, recording the development of a feature on a clock no human will ever live long enough to see complete. The second consequence is the consequence we have already touched on. The rings are tipped. Almost all of the moons of Uranus orbit in the equatorial plane, which means their orbits are tipped too. Looking at the Uranian system from the inner solar system, you do not see a flat disk with a planet in the middle of it. You see a target. Vertical concentric circles around the planet, with the moons swinging through them on near circular paths. Webb's images make this orientation obvious, in a way no Voyager image really did, because Voyager flew through the system at a specific geometry that did not show the perpendicularity of the rings to the line of sight. The third consequence runs even deeper. We will get to it more fully when we talk about the magnetic field. But the field too is wrong in a way that points to the same cause. A planet does not tip itself over. A spinning sphere, especially a giant spherical fluid body that took millions of years to form by accretion from a swirling disk of gas and dust, does not simply choose to rotate sideways. Conservation of angular momentum will not allow it. Whatever set of conditions originally produced, the spin will produce a spin axis broadly perpendicular to the orbital plane, because that is the geometry the formation disk itself had. To get a planet rotating 97 degrees off vertical, you have to do something to it after it has formed. You have to apply a large torque from outside. The natural candidate, almost from the moment anyone first noticed Uranus's tilt, is the same candidate that produces almost every other weird-looking planetary detail when you do not have a better idea. A giant impact. A collision early in the solar system's history with another large body, large enough to deliver the angular momentum required to tip the planet on its side small enough that the planet did not break apart entirely. That kind of collision is not a fantasy. We have very good evidence that something analogous happened to the Earth in the first few 100 million years of our own planet's history, when an object about the size of Mars struck the proto-Earth and the resulting debris coalesced into the Moon. The moon-forming impact is now the standard explanation for everything from the Moon's composition to the way the Earth's mantle is layered. There is no reason something similar could not have happened on a larger and more violent scale at Uranus. In 2018, a team led by the British planetary scientist Jacob Kegerijs published a paper in the Astrophysical Journal that took the giant impact hypothesis for Uranus and ran the math on it. They used a type of simulation called smoothed particle hydrodynamics, a technique that breaks the bodies involved into millions of small fluid parcels and lets each parcel feel the gravitational and pressure forces from all the others, computing the system's evolution in 3 dimensions over time. They simulated dozens of different impact scenarios for Uranus, different sizes of impactor, different angles of attack, different velocities. They asked in each case whether the simulated outcome looked anything like the Uranus we actually see today. The results converged on a fairly clear picture: an icy protoplanet with a mass between roughly 1 and 3 Earth masses, striking proto-Uranus at a grazing angle of around 60 degrees relative to vertical, at a velocity consistent with what you would expect for a body falling inward from the outer reaches of the proto-solar system, can produce both the observed 97-degree tilt and the broad structural properties of the modern Uranus system, including the compact prograde moon system and the formation of a debris disk that settles into the modern ring structure within roughly 10,000 years of the impact. The impactor itself either spirals in and becomes part of the planet, or is fragmented and partially absorbed and partially flung onto a wide orbit. The energy of the collision deposits a tremendous amount of heat into the body of the planet, much of which radiates away over the next few 100 million years. There are subsequent papers that refine the picture. A team led by Christian Reinhardt in 2020 published a follow-up in monthly notices of the Royal Astronomical Society that confirm the impact angle and impact velocity ranges with a different code and a different set of simulations. The hypothesis has been tested, retested, varied, it survives. The single impact picture for Uranus's tilt is now mainstream. The data fits, the numbers work, which means that, at the dawn of the solar system, about 4.5 billion years ago in roughly the orbit where Uranus now circles the Sun, 2 large icy bodies collided. One of them broke apart, the other was knocked in a single brutal moment onto its side. The debris from the collision spent the next 10,000 years organising itself into a disk, and that disk became the ring and moon system we now study. And then the wounded planet slowly, over 4 billion years, did not recover. It is still on its side. It still has the rings the collision produced. It still has the magnetic field the collision left in a kind of structural disarray. It is, in the most literal sense, scar tissue. Almost everything distinctive about Uranus, from the tilt that defines its seasons to the moons that orbit it to the field that wraps it, is the durable signature of a single ancient incident. Hold that phrase, a wound 4 billion years old. We are going to come back to it. There is more than one place on this planet that carries the mark. Part 7. The year-long polar night. If you have ever watched a sunrise, you know how it feels. The slow violet of the eastern sky, the first thin band of orange, the way the air shifts in the seconds before the disk clears the horizon, the world quietly trading the cold of night for the soft heat of morning. Sunrises are so familiar, so woven into how we tell time and how we think about days, that it is genuinely strange to imagine a place where they do not happen. Uranus is that place. For long stretches of its year, in large parts of its hemispheres, no morning ever arrives. The planet's orbital period is 84 Earth years. That is the time it takes Uranus to circle the Sun once. 84 years is already a long time. Most people who watch a Uranian year begin will not be alive to watch it end. Children born today in the mid-2020s will be in their 80s before Uranus completes its current trip around the Sun. So already, the unit of time we're talking about is longer than a human life. Stretch the year across the 97.77-degree axial tilt. The planet rotates on its side. As Uranus moves through its orbit, the pointing of its rotation axis stays roughly the same relative to the stars, which means at the moment of one solstice, one of the poles is aimed almost straight at the Sun. A quarter of a Uranian year later, 21 Earth years on, the planet has moved a quarter of the way around the Sun, and now the equator is aimed at the Sun, and the poles are aimed perpendicular to it. Equinox, with brief day-night cycles across all latitudes. Another 21 years later, the other pole is aimed at the Sun. 21 years after that, the equator is aimed at the Sun again, and the cycle has come full circle. Now imagine you're standing on Uranus's lit hemisphere, midway through one of the polar solstice intervals. Imagine, for the sake of the picture, that you have somehow survived the cold and the chemistry, that you have a place to stand that does not exist because there is no real surface that you can look up. The Sun is a small disk. From Uranus, our Sun appears about a quarter of the angular size it has from Earth. It is dim. The full daylight on Uranus is about 1/367th the intensity of a sunny afternoon on Earth. Noon on Uranus is dimmer than the moments just after sunset on a clear summer evening at home. It is what an ordinary backyard looks like at the very edge of dusk, when the sky has gone from blue to violet and is about to go to grey. But the Sun is not setting. It is not moving toward any horizon. It is fixed almost in the same patch of sky. Because the planet rotates beneath your feet, the Sun does make a slow, lazy circle in the sky once every 17 hours and 14 minutes, the rotation period of Uranus. It loops. It does not set. It loops again. It does not set. It loops a third time. The 17-hour rotation comes and goes. The Sun stays up. The next day starts. The next day. The next day. The next year. The next decade. For 21 Earth years, this is the configuration. The dim Sun fixed near the top of the sky, looping over itself, never falling toward the horizon, never giving way to a night. The light is the steady twilight intensity. The air, if there were air to feel, would never do the morning-evening trade. There is no diurnal rhythm. There is no morning. There is no evening. There is only the slow 21-year stretch of permanent shrunken day. On the opposite hemisphere, at exactly the same time, the reverse situation holds. The same patient absence, mirrored. 21 Earth years of darkness. The Sun in that hemisphere is below the horizon for the entire duration. It does not rise. It does not glow at the edge of the sky. There is no first hint of dawn. No slow violet, no morning band of orange. There is only the unbroken dark, and whatever cold, faint, immobile starlight the universe provides to fill it in. If you were born on the wrong hemisphere of Uranus, at the wrong moment of the planet's 84-year cycle, you could grow up, learn to walk, learn to read, fall in love, have children, watch them grow old, and die, and never once see the Sun come up. The very idea of sunrise would be, for your whole life, a thing told to you by other people, something you read about, something the lucky ones on the other side of the world watched happen, decade after decade after decade, while above you it stayed dark. It is, as a thought experiment, deeply unsettling. Sunrise is the most basic unit of human time. We measure our days by it. Our circadian rhythms are tuned to it. 21 years of polar night is longer than the span we usually call a generation. It is longer than the average career. It is longer than the time most people spend in the home of their parents before moving out. It is longer than the lives of most pets. It is longer than the longest natural human pregnancy by orders of magnitude. It is, in pretty much every meaningful sense, a long time. And it is happening on Uranus, twice every Uranian year, and has been happening for billions of years. The polar cap that Webb is so dramatically watching season by season is the visible signature of this strange seasonal cycle. As the North Pole tips toward the Sun in the run-up to the 2028 solstice, the air above the pole heats slightly, and chemical compounds in the upper atmosphere, methane, ethane, acetylene, ammonia traces, are processed by ultraviolet light from the Sun into a hazy layer that, in near-infrared, glows bright. The cap brightens as the pole moves into the Sun's light. The cap fades as the pole turns away again. The polar vortex turns under the cap, anchored to the rotation axis, churning slowly in the cold air above. There is no other planet in the solar system that does this. There is no other planet whose seasons are this long. There is no other planet where you could miss every sunrise of your life by being born on the wrong side at the wrong time. Uranus is the only world we know that does that, and Webb, by sitting patiently at its observatory point 1.5 million kilometers from Earth, is the first instrument in human history that has had a good enough eye to watch the seasonal weather of a planet on a clock longer than a human career. It will not, in any single human's lifetime, see the entire cycle. The current Webb mission is expected to run, in baseline plans, for somewhere between 5 and 20 years. That covers, at the high end, a single full season, not even a quarter of a Uranian year. The fully resolved seasonal monitoring of Uranus is a multi-generational project. People who are not yet born will be the ones who finally complete it. That is the timescale we are now on when we look closely at this planet. The patient timescale, the one that requires the kind of patience the universe itself rewards, and the disguise underneath the photograph started finally to come off. We have walked through the tilt. We have walked through the year. The next thing to walk through is the cold. Because at the temperatures we're about to talk about, language itself starts to give out, and you realize that the dimness of the sky and the slowness of the years are only the prelude to something genuinely without comparison anywhere else in our solar system. Part 8. The coldest place. Of all the worlds in our solar system, Uranus is the coldest. Not the farthest from the Sun, not the slowest in its orbit, not the most distant any of our spacecraft has ever travelled. The coldest. And that distinction is not a small thing, because the coldest planet is the one whose chemistry and physics are most strained against the basic intuitions that our warm-blooded selves carry around. The minimum measured temperature at the tropopause of Uranus, the boundary between the lower atmosphere where weather happens and the upper stratosphere where temperatures begin to climb again because of solar UV processing, is about 49 degrees on the Kelvin scale. 49 Kelvin translates to roughly minus 224 degrees Celsius, or, in the units most familiar to many of you watching, roughly minus 371 degrees Fahrenheit. Those numbers are so far below the range our daily vocabulary covers that they almost stop meaning anything. 370 below zero on the Fahrenheit scale is a number you have to translate carefully to feel. Let me try to give it some scale. The coldest temperature ever measured directly on the surface of Earth, anywhere, was at Vostok Station, in the interior of the Antarctic Plateau, on the 21st of July 1983. The reading was minus 89.2 degrees Celsius. In Fahrenheit, that is about minus 128.6. That is the worst Earth has ever done. That is the kind of cold that on direct exposure would kill an unprotected human being in seconds. That is the kind of cold that freezes camera mechanisms, snaps steel cables, and causes the air in your lungs to feel like it is shredding the inside of your chest. Uranus is roughly 135 degrees colder than that. Not 135 degrees colder than a comfortable indoor temperature. 135 degrees colder than the very worst cold our planet has ever been measured at. Antarctica, at its coldest moment ever recorded, would feel like a balmy summer afternoon if you somehow walked through it after coming up from the cloud deck of Uranus. The relative warmth would feel real. That is how extreme this is. And this is not a quirk of seasonal timing or a local cold pocket. This is the upper atmosphere baseline. Uranus, by the time Voyager and ground-based observations had pinned down its temperature profile in the late 1980s and early 1990s, was the coldest planet anywhere in our system. Here is the part that genuinely puzzles the people who study it. Neptune is farther from the Sun than Uranus, substantially. Neptune is, on average, about 30 astronomical units from the Sun, while Uranus is about 19. Neptune is roughly 50% farther out. Less sunlight reaches Neptune than reaches Uranus. By the simplest possible energy balance reasoning, Neptune should be the colder planet. The amount of solar power per square metre falling on Neptune's upper cloud deck is a little less than half of what falls on Uranus's, and so all else being equal, Neptune's temperature minimum should be lower. It is not. Neptune's minimum, by careful measurement, is about 51 to 53 Kelvin, a degree or two warmer than Uranus. Neptune is the farther planet and it is the warmer planet. Uranus is the closer planet and it is the colder one. The reason, as far as anybody can tell, has to do with the difference in their interior heat engines. Every giant planet, when it forms, accretes a tremendous amount of gravitational potential energy as it pulls material in. That energy becomes heat in the interior. Once formed, the planet slowly radiates that heat away over billions of years. Jupiter is still leaking enormous amounts of formation heat. Jupiter radiates more than 1.5 times the energy it receives from the Sun. Saturn likewise. Neptune, despite being smaller and older, still radiates about 2.5 times what it receives from the Sun. Neptune's internal heat engine is alive, churning, leaking warmth steadily out through its atmosphere. Uranus does not. Careful measurements of Uranus's energy budget, from Voyager's Iris infrared spectrometer in 1986 and from ground-based and Hubble follow-ups across the following decades, indicate that Uranus radiates approximately 1.06 times as much energy as it absorbs from the Sun. That number is essentially indistinguishable from energy balance. The planet has, for all practical purposes, no detectable internal heat output. Its furnace, in the sense that we mean the word for Jupiter or Neptune, is switched off. Why? Nobody knows for sure. The leading hypothesis, perhaps unsurprisingly, points back to the same ancient incident we just talked about. The giant impact that tipped Uranus is the same impact that, in the simulations, would have dramatically reorganized the planet's interior. One possibility is that the collision punched a hole in the layered structure that would otherwise have trapped heat in the deep interior, allowing the planet's heat to radiate away much faster than for an undisturbed gas giant. Another is that the collision disrupted whatever convective patterns would normally have ferried heat from the deep interior outward, leaving the heat sealed in below a stubbly stratified blanket. Either way, the inference is the same. The same event that tipped the planet broke its heat engine. The wound runs that deep. That, in turn, is why Uranus is so cold. The Sun is not enough on its own to warm the upper atmosphere any more than it does, and there is no significant internal heat coming up from below. Uranus exists in effect with no fire of its own. It is what Neptune would be if you took Neptune's furnace away. Sit with that for a moment. There is a planet in our own solar system, the third largest by diameter, that has been quietly freezing for 4 billion years because something hit it hard enough to break the engine that would normally have kept it warm. The cold is not a quirk. The cold is a symptom. The cold is the planet still grieving the impact, in a sense, in the only way a planet can grieve, by radiating away the heat it can no longer replace. The numbers we have for now all come from instruments far away. The Voyager Iris data was collected in those 6 hours in January 1986. The ground-based mid-infrared imaging and the Hubble temperature retrievals have refined the numbers but not changed the picture. The dedicated Uranus orbiter and probe mission, when and if it flies, and we will talk about it in the last part, will be the first chance to drop an instrument package directly into Uranus's upper atmosphere and measure the temperature profile from the inside. Until then, every number we have for how cold Uranus actually is, at every altitude through its atmosphere, is a number inferred from a distance. The fact that we know it to such precision, the fact that we can tell with confidence that this is the coldest planet in our system, and the temperature gap between Uranus and Earth's worst cold is more than 135 Celsius, is the result of careful instrument design and careful inference, and the willingness to look hard. We just had to look closer. The Sun's father planet is the warmer one. The closer planet is the deep freeze. The truth is upside down from the obvious, and only attention reveals it. Part 9. The smell. Up to this point, we have been talking about Uranus in terms of pictures and numbers, the photograph, the tilt, the year, the cold. There is one more, almost intimate thing about the planet that any honest tour of it has to include. It is genuinely strange to say out loud, but the upper clouds of Uranus, the ones we can see, the ones in those Webb infrared images, almost certainly smell very strongly of rotten eggs. In 2018, the team I mentioned earlier, led by the Oxford astronomer Patrick Irwin, and using the Gemini North 8.1 metre telescope on Mauna Kea, published a paper in the journal Nature Astronomy with what sounds at first like a small technical result. They had detected hydrogen sulfide in Uranus's upper cloud deck. They had measured its abundance, a small amount on the order of 0.5 part per million at the relevant altitude, give or take. They had confirmed something that had been suspected for decades but never directly observed. The clouds at the top of Uranus's atmosphere are made in significant part of ice particles of hydrogen sulfide. Hydrogen sulfide is a small molecule. Its formula is 2 hydrogen atoms attached to a single sulfur atom. The molecule is heavier than oxygen, lighter than carbon dioxide. It is unstable in the presence of oxygen-rich atmospheres because it reacts to form water and elemental sulfur, which is why it is not common in Earth's air. It is, however, common in environments where oxygen is scarce and other chemistry dominates. Hot springs produce it. Volcanic vents produce it. The interior of decomposing biological matter produces it. Marsh gas often contains it. The cracked shell of an old hard-boiled egg releases it. It is, almost universally, the molecule that human beings associate with the smell of rot. Our noses can detect hydrogen sulfide at concentrations down to about 0.5 part per billion in air. We are extraordinarily sensitive to it, in the way that animals tend to be sensitive to molecules that signal something dead or rotting nearby. We do not like the smell. We are evolutionarily configured not to like the smell. It is a survival reflex, and those are the clouds at the top of Uranus. It is worth being precise here. Nobody is going to stand on Uranus. There is no place to stand. The clouds are made of frozen hydrogen sulfide ice particles, not breathable gas, suspended in an atmosphere that is mostly hydrogen and helium and methane. The temperatures are so low that the smell would not necessarily reach a hypothetical person at full strength, the way it would in warm air on Earth. But if you could somehow, in defiance of all physics, descend into the upper cloud deck of Uranus in some imaginary protected pod and crack a window for the briefest possible moment, the first thing that would register in the cold air pouring in, before your sensors registered the cold itself, before the pressure of the atmosphere registered through the open window, before any of the other things, would be the smell. The unambiguous chemical announcement of decay. Hydrogen sulfide above some threshold and your nose says rot. Below the threshold and your nose says nothing. The threshold is 0.5 part per billion. Uranus's cloud deck is roughly 1,000 times that. The smell, in any physically reasonable warm air analogue, would be overwhelming. Irwin, when the press team at the Royal Astronomical Society wrote up the result for general audiences, gave a quote that has been repeated in every news article about Uranus's atmosphere ever since. An unfortunate human descending through Uranus's clouds, he said, would meet very unpleasant and odoriferous conditions, the polite version. The honest translation is that the smell would be the first thing you registered, and likely also the last, because the cold and the pressure and the suffocation would finish their work very shortly afterward. He noted in a follow-up clarification that the suffocation and the cold would take their toll long before the smell ever had a chance to ruin your day in any meaningful sense. The smell, in other words, is one of the lesser hostilities of Uranus. It is the planet's small, almost embarrassing detail on a list of much larger and stranger ones. There is something quietly funny about a planet that smells like a cracked egg. It is the kind of fact that, When somebody mentions it at a dinner party, it makes everyone else briefly forget about the multiverse or dark matter or whatever else they had been discussing. People remember that detail. It is small enough and specific enough to stick. For all the cosmic scale strangeness of Uranus, the tilt, the cold, the diamond rain we're about to get to, the thing that often lodges in human memory is the rotten egg. It is the disguise of seriousness that the universe occasionally allows itself, a wink in the middle of the cosmic horror. But the chemistry also tells a deeper story. The reason hydrogen sulfide is exposed at the top of Uranus's cloud deck, rather than locked away below an ammonia layer the way it is on Jupiter and Saturn, has to do with the temperature structure of the atmosphere. On Jupiter and Saturn, the atmosphere is warm enough at the relevant pressures that ammonia condenses out as ice at a level above where hydrogen sulfide would. The result is that the cloud deck we see on Jupiter and Saturn is ammonia ice and ammonium hydrosulfide ice, with the pure hydrogen sulfide tucked away in deeper layers we cannot see directly. On Uranus and Neptune, by contrast, the atmosphere is so cold that ammonia freezes out at a deeper pressure level than it does on Jupiter, while hydrogen sulfide stays gaseous longer because of the planet's chemistry. The result is a cloud deck dominated at the top by hydrogen sulfide ice and methane condensation. The planet's smell, in other words, is a fingerprint of how cold the chemistry runs. Uranus smells like rot because the warm chemistries that would mask the smell never get a chance. The chemistry also gives us a clue about the planet's bulk composition. Uranus and Neptune are not gas giants the way Jupiter and Saturn are. They are ice giants. The category was named for the fact that, in their interiors, the dominant materials are not hydrogen and helium, but the ices of planetary science, water, methane, and ammonia, under conditions of such extreme pressure that the very meaning of solid, liquid, and gas starts to break down. Hydrogen sulfide in the atmosphere is consistent with that bulk composition. It is a small, light, volatile molecule that survives the conditions of an ice giant atmosphere where the ammonia and water are tied up below. The smell, in this view, is part of how we tell what kind of planet we are looking at. Uranus, by the chemistry of its clouds alone, would be classified as an ice giant if all you had was the smell, which is not the way astronomers tend to phrase it in papers, but the underlying logic does not change. So we have a planet that lies on its side, that has years longer than human lives, that is colder than the worst Earth has ever managed, and now, on top of all of it, that smells like a cracked egg in the sun. It is, in a way, the most absurd planet in our solar system. Almost everything about it is wrong in a different direction from everything else, and we have not even reached the bottom of it yet. The smell, the cold, the tilt, the year, all of these are surface features of a world whose interior, when you go deep enough, becomes something that, when you finally describe it carefully, sounds less like physics and more like poetry. The next part is what is happening underneath the clouds. We're going to fall slowly into Uranus, and what waits down there is, well, we will get to it. Part 10. The Bottomless Ocean and the Diamond Rain. Take a breath. Settle in. The next part of this video is the part where we leave the visible disk of Uranus and go down. There is no surface to land on. There is no floor to break. The atmosphere does not end the way Earth's does, at a clean line between gas and rock. It just gets thicker. The pressure climbs, the temperature climbs, the chemistry shifts, and eventually thousands of kilometers below the top of the clouds, you reach a place that, the more carefully scientists describe it, sounds less and less like anything we have words for. We will use the words we have slowly, but the picture, in the end, is one that has to be held in your mind rather than spoken outright. Imagine, then, falling into Uranus, not as a spacecraft, as an idea, as the listener of a video. The top of the cloud deck is where Webb's eye stops. The visible disk is the bright haze cap and the methane ice storms and the hydrogen sulfide clouds we just talked about. As you descend below that, the pressure rises, and the chemistry changes layer by layer. ammonia clouds, condensing at slightly deeper levels than the hydrogen sulfide cap above. Water clouds, deeper still, where the temperature finally rises into a range where water vapour can condense into ice or droplets despite the planet's overall cold. Then, beneath all of that, the cloud structure ends. The atmosphere becomes a thick, hot, dense, electrically conductive medium that is not really a gas in any useful sense and is not really a liquid either. It is what we would call, in the planet science literature, a supercritical fluid, a state of matter where the distinction between gas and liquid loses its meaning and the substance behaves as a single dense flowing medium. Imagine air, but compressed and warmed until it has the density of water and starts to behave like it does. That is what you are falling through now. Falling, here, is also a slightly slippery word. The increasing density and pressure mean that, well before you would have crashed, you would have stopped falling and started swimming, and then, fairly soon after that, stopped swimming and started being crushed. The pressures inside Uranus's mantle are millions of times Earth's surface pressure. A spacecraft would not crash here. It would simply be squeezed, layer by layer, until it stopped being a spacecraft. There is no impact. There is no bottom in the sense that human intuition wants. There is only a continuous, slow, deepening compression. And the falling as an idea continues, because what we are tracking is not a survivable trajectory, but a journey through layers of the planet's interior. About a third of the way to the centre of Uranus, the medium has reached the conditions that planetary scientists call the mantle. This is where the bulk of the planet lives. It is not water, exactly. It is not ammonia, exactly. It is not methane, exactly. It is a hot, dense, churning mixture of all three. Water plus ammonia plus methane, at pressures of tens to hundreds of gigapascals, that is, hundreds of thousands to millions of times Earth's atmospheric pressure, and at temperatures of thousands of Kelvin, hot enough to glow in the dark if there were anywhere you could look at it from. The whole interior of Uranus, beneath the visible cloud deck, is essentially one giant, hot, electrically charged ocean. An ocean thousands of kilometers deep. An ocean that has no surface above and no floor below. An ocean that has been turning, in convective patterns we can only model, for 4.5 billion years. You could not drown in this ocean. Not because it is not deep, but because you would be crushed and cooked long before the question of drowning came up. The medium is not water in any sense your body could recognize. It is something more strange. It is, if you let the language stretch a little, the deep middle of a planet in its most literal possible meaning. And inside this hot, dense ocean, something is happening that scientists have only recently confirmed in laboratory experiments, and that, when you say it out loud, sounds like a sentence that should be in a fairy tale. It rains diamonds. I am not being poetic. I am not stretching a metaphor. The conditions of pressure and temperature in the mantle of Uranus are very nearly identical to the conditions under which, in carefully calibrated laboratory shockwave experiments, scientists have watched, in real time, individual carbon atoms in methane molecules tear apart from their hydrogen partners and reorganize themselves into crystal lattices of solid diamond. The methane in Uranus's mantle, when squeezed to the right pressures and heated to the right temperatures, breaks. The carbon precipitates out as tiny diamond crystals. The hydrogen, now alone, joins the rest of the planet's hydrogen-helium budget elsewhere. The diamonds, because they are denser than the medium they crystallized in, sink. They begin a slow, silent descent through the hot ocean of the mantle, falling toward the core of the planet, which lies, depending on the model, somewhere between 14,000 and 17,000 kilometers deeper still. They take, in the most careful estimates, hundreds to thousands of years to make the trip. Trillions of carats of diamond, at any given moment, are in active descent through the Uranian mantle. The laboratory experiments that confirmed this picture were led by Dominic Krauss, a physicist who at the time was working at the Helmholtz Zentrum Dresden-Rossendorf in Germany, and used the Linear Coherent Light Source, the LCLS, a giant X-ray laser at the SLAC National Accelerator Laboratory in California. Krauss and his team published their results in Nature Astronomy in 2017. The paper bore the title Formation of Diamonds in Laser-Compressed Hydrocarbons at Planetary Interior Conditions, which is a bland title for what is, in plain language, an experiment in which scientists made it rain diamonds inside a laboratory apparatus by hitting a pellet of plastic with shock-compressed laser light. The plastic was polystyrene. The shock waves were calibrated to produce, briefly, the temperature and pressure conditions that the team had calculated would exist tens of thousands of kilometers below Uranus's cloud tops. The X-ray laser, while the shock was active, took a series of extremely short diffraction measurements of the compressed material. The patterns matched the signature of crystalline diamond. Subsequent follow-up papers, including work led by Daniel Hartley in 2022 and Sebastian Friedrich in 2020, refined the pressure-temperature thresholds and made the picture sharper. The diamonds in the laboratory shock formed in nanoseconds. The diamonds in Uranus's mantle, presumably, have been forming for billions of years. There is no way currently to confirm this picture by direct observation. We cannot see into Uranus's mantle. The diamond rain is real because the chemistry is real, the conditions are real, the laboratory matches the chemistry, and the result is what the chemistry predicts. The picture is consistent with everything else we know about the planet's bulk composition, its mass, its density, and its size. The mainstream picture among planetary scientists is that diamond rain is, very plausibly, occurring inside Uranus right now. It is one of the most striking applications of laboratory shock physics to planetary science that has ever been done. Let me try to give you the picture properly. Imagine then, not a storm, not a downpour, something slower than that, something quieter. In the deep mantle of Uranus, in a vast hot ocean that has no surface above or floor below, tiny crystalline diamonds are forming one by one in the slow chemistry of broken methane. They form silently. The hot, dense fluid around them is opaque to anything you could call light. The pressure they form under would instantly crush any device or eye that might have been built to witness them. They are dense enough to sink. They begin to descend. They do not fall through air. They drift through the thick, dark, hot medium of the mantle, falling, 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 for hundreds or thousands of years, toward a core thousands of kilometers further down. There are an unimaginable number of them, trillions of carats, quadrillions of crystals. They have been falling in this slow, silent fashion for billions of years. They are still falling now while you watch this video. They will be falling tomorrow. They will be falling 100 years from now. They will be falling, in fact, in some configuration, until the planet itself dies. It is one of the strangest, most extreme, most genuinely beautiful things in our solar system. A permanent silent storm of diamonds, raining through a hot, dense dark, falling forever toward a centre no light has ever touched and no eye will ever see. The most beautiful thing in the solar system, happening in the most hostile place we know, witnessed by no one, lasting essentially forever. Sit with that for a moment. Take whatever calm you find in it. It also captures in a way the whole character of Uranus. The planet does not show off. It does not announce. It does not stage any of its strangenesses for any visitor's benefit. It quietly does the most extreme things in the cold and the dark, behind a calm photograph, and lets the universe rain diamonds in private. We had to look very carefully, with very expensive instruments, in very specific kinds of light, to find out it was happening at all. The disguise extends all the way down. We have walked down through the cloud deck, through the mantle, into the diamond rain. The remaining layer is the core itself, a small rocky iron heart at the very middle, almost certainly hot enough to glow in the dark if you could ever get to it, almost certainly the densest single thing in the Uranian system. We do not know its size to high precision. We do not know its temperature to high precision. We do not know its composition to high precision. What we know is that beneath the diamond rain there is something solid and small and old and the rest of the planet is built around it. The Uranus orbiter and probe mission, when it flies, will try to constrain the core's properties by gravimetric and seismic measurements. Until then, the core is the deepest secret the planet still keeps, the place even the diamonds are, in their slow, patient way, falling toward. The mantle is also where the planet's other great mystery lives. Because the magnetic field, that strange tilted, offset, tumbling field we have been hinting at, is generated in the mantle, not in the core. The mantle is where the dynamo runs, and the way the dynamo runs is the next layer of the wound. Part 11. The Field That Tumbles. A planet, almost any planet, has a magnetic field. Earth's field is the obvious example. It surrounds us, deflects the solar wind, traps charged particles in radiation belts above the upper atmosphere, and produces auroral displays at high latitudes when bursts of charged particles slam into the air and excite atoms to glow. Compasses point along Earth's field. Birds and certain other animals use Earth's field to navigate. The field is generated by the slow churning of liquid iron in the planet's outer core, which produces electric currents, and, by induction, the planetary magnetic field. The result, in Earth's case, is what is called a dipole field, a field whose shape is roughly that of a bar magnet, with two opposite poles, the north magnetic pole and the south magnetic pole, lined up close to but not exactly with the rotation axis. Earth's dipole tilt, that is the angle between the magnetic axis and the rotation axis, is about 11 degrees. Earth's dipole offset, the distance between the magnetic centre and the geometric centre of the planet, is small, on the order of a few hundred kilometres, less than a tenth of the radius of the planet. That is the standard. A clean dipole, mostly centred, mostly aligned with the rotation. It is the picture every planet in our solar system except Uranus and Neptune more or less obeys. Jupiter's field, Saturn's field, Mercury's field, all of them are dipoles with tilts in the single digits, all of them more or less centred. Now, Uranus. Uranus's dipole tilt, the angle between the rough magnetic axis and the rotation axis, is 58.6 degrees. Read that out loud. 58.6 degrees, compared to Earth's 11, compared to Jupiter's tiny 10. Uranus's field is tilted more than 5 times as far off axis as Earth's. It is so tilted that, for some moments of the planet's rotation, the magnetic poles are actually closer to the equator than to the rotation poles. The whole concept of magnetic north and magnetic south becomes almost meaningless on Uranus. The poles wander, depending on which face of the planet is turned toward the Sun, across a range that no other major planet's field ever covers, and the tilt is only the first weirdness. The dipole is also offset. The magnetic centre of Uranus is not at the geometric centre of the planet. It is shoved roughly a third of the planet's radius toward the southern hemisphere, roughly 8,400 kilometres off-centre. The field, in other words, is not symmetric. The southern surface field strengths, where the magnetic centre sits closer to the surface, reach approximately 100,000 nanoteslas at points on the disk. The northern surface field strengths, where the magnetic centre is far from the surface, can be as low as around 10,000 nanoteslas. A factor of 10 difference, just by being on one side of the planet versus the other. It is, structurally, as if somebody grabbed the planet's magnetism and yanked it loose from its mooring. The result is a magnetosphere that does not behave like Earth's, or Jupiter's, or Saturn's, or Neptune's. As Uranus rotates, once every 17 hours and 14 minutes, the magnetic field tumbles with it, and the shape of the magnetosphere changes hour by hour. There are moments when the magnetic structure looks something like a normal magnetic configuration. There are moments when it looks like nothing else we know. There are moments when the magnetic gates that should channel solar wind particles in toward the planet open wide, and there are moments when they close almost entirely. The magnetotail, the long stream of magnetic field stretched out behind the planet by the pressure of the solar wind, is not a simple cylinder, it is a corkscrew. Voyager 2's plasma instruments, in 1986, measured the corkscrew structure directly, and the scientists analysing the data spent years afterward arguing about exactly what they had been looking at. The aurorae that flicker on Uranus, the ones Hubble first caught in 2011, are weak, displaced and weird in shape because of all this. They do not form clean rings at the poles. They form patches and arcs at strange latitudes, sometimes very close to the equator, where the tilted magnetic field happens to intersect the upper atmosphere at that rotational phase. Webb refined the picture by imaging Uranus's aurorae in infrared in 2023 and 2024, picking up signatures of charged particle precipitation at locations consistent with the tilted multipole field model. Uranus's auroras, more than any other planet's, are a direct visualization of the planet's broken field geometry. Why is the field this way? The Voyager-era picture was that the field had to be generated by some kind of dynamo in the planet's interior, but the geometry, strongly tilted, strongly offset, did not look like the kind of dipole geometry a deep convecting core would produce. Modern interpretations, developed across the late 1990s and the early 2000s and refined since, suggest that the field is generated in a relatively thin shell of convecting material in the outer mantle rather than in a deep dipole-producing core. The shell is not very thick, perhaps a few thousand kilometers deep, and the dynamo it runs is, in shape, much messier than a clean dipole. The result is a field rich in higher-order components, quadrupoles, octupoles, and higher, rather than dominated by the simple dipole geometry that most other planets show. The material in that thin convecting shell, by all current modelling, is almost certainly some combination of superionic water and ammonia. We talked about diamonds earlier. Superionic water is the other strange phase of matter you find inside ice giants. Superionic water is what you get when you take ordinary water, H2O, and squeeze it under pressures of tens to hundreds of gigapascals while heating it to thousands of Kelvin. Under those conditions, the oxygen atoms lock into a crystalline lattice, like a solid, while the hydrogen ions break free and flow through the lattice like a liquid. The result is a phase of matter that is simultaneously solid and liquid in different respects. It is mechanically rigid, in the sense that the oxygen lattice does not flow, but it is electrically conductive in the sense that the hydrogen ions move freely. An electrical conductivity, combined with convective motion in a planetary interior, is exactly the ingredient required to run a dynamo and generate a magnetic field. This was predicted originally in a paper by Carlo Cavazzoni and colleagues in 1999. It was confirmed in the laboratory 2 decades later, in laser shock experiments led by Marius Millo at the Lawrence Livermore National Laboratory, with results published in Nature in 2019. Vitali Prakapenka's group at the Advanced Photon Source contributed further pressure temperature refinements in 2021. The superionic phase of water is now an established part of planetary interior modelling. Uranus's magnetic field is, in the leading current picture, generated by a thin shell of superionic water-ammonia material convecting in the outer mantle, with a dynamo geometry that does not produce a clean dipole. The remaining question is why the shell is configured the way it is. Why so strongly tilted? Why so far off-centre? Once again, and you should be hearing the same chord struck for the 3rd time in this video, the leading hypothesis points back to the same source. The same giant impact that tipped the planet, that switched off its heat engine, also disrupted the interior structure deeply enough that the convecting shell that should have produced a clean dipole instead produces this multipole disarray. The wound is not just on the planet's surface. The wound goes all the way to the planet's heart, a wound 4 billion years old. Said the first time about the tilt of the rotation axis, said the second time about the heat engine, said now, with deeper meaning, about the magnetic field itself. The damage is structural, the damage is total, the damage runs through every distinctive thing about this world. When you take all 3 together, the tilt, the cold interior, the broken field, you're not really looking at a planet that happens to be strange in three independent ways. You're looking at the durable signature of a single ancient incident, expressed in three different parts of the same body. Whatever struck this planet did not just tip it over. It scrambled it from the inside out, and 4 billion years later, the planet still has not found its balance. The wound, in other words, has never healed. The planet has spent the entire history of the solar system not recovering. Most planets carry the scars of their formation as features of their landscape. Uranus carries them as structural damage. There is no other planet quite like this anywhere we have looked, in our system or in the catalogues of exoplanets we are slowly building. Uranus is the closest example we have to a planet that something happened to, and almost as if to apologise for what was done to it, the universe has given it some of the strangest beauty in our system. Beside the wounds there are the rings and the moons, and a cliff that, if you fell off it, would take you 10 minutes to reach the bottom. We've arrived at the part of the video where the strange weight of Uranus finally lightens, a little, into something almost lovely. Part 12. Sideways rings, hidden moons, a tall cliff. The Uranus we have been describing, the tilted, frozen, dimly lit, diamond-veined, field-shattered Uranus, is also a planet with an extraordinary household. Around it orbits one of the most elegant ring systems in the solar system, even if it is dark and faint and easy to miss. Around it travels a small fleet of moons named, not after gods or natural world figures the way most other planetary moons are, but after the characters of Shakespeare and the poet Alexander Pope: Ariel, Umbriel, Titania, Oberon, Miranda, Puck, Caliban, Sycorax, Belinda, Rosalind, Cordelia, Ophelia, Mab, Cupid, Perdita, a frozen literary court orbiting the sideways king in the dark. There is something deeply, gently beautiful about it, if you sit with the names long enough. There are, as we have already mentioned, 13 named rings, 11 of which Webb captured in a single composite image in 2023. The rings are old and dark, almost certainly composed of water ice contaminated by radiation-processed organic compounds, which over geological time have darkened to something blacker than charcoal. Their reflectivity is, depending on the ring, somewhere between 2 and 4%, which means that 96 to 98% of the light that hits a ring particle is absorbed rather than reflected. For comparison, ordinary asphalt reflects about 10 to 12%. The rings of Uranus are darker than the road outside your house. They are darker than soot. They are easy to miss in any imaging that does not have very high contrast against the dark sky behind, which is part of why most space documentaries you have ever seen leave them out of the establishing shot. They are too faint in the visible light pictures most television uses to bother including. Webb showed them anyway, because Webb does not work in visible light. Webb works in the near and mid-infrared, where the rings are still dark but the contrast against the colder background sky is better, and where the ring's own faint thermal emission can be picked up directly. In Webb's December 2023 image, all the major rings are crisp and clear. The brightest of them, the Epsilon ring, runs around the outside of the system, shepherded on its inner edge by the small moon Cordelia and on its outer edge by the small moon Ophelia. The two moons keep the ring particles confined to a narrow band by their gravity, a textbook example of shepherd moon dynamics, first really demonstrated at Uranus by Voyager and now refined by Webb. There are inner narrower rings, faint but visible. There is the faint dusty Zeta ring close to the planet, which we have already discussed. There are the outer dusty Mu and Nu rings that Hubble found in 2003 and 2005, very wide and very diffuse, almost more like haze than rings. All of these rings, because of the planet's tilt, are tipped on their side. They do not lie flat the way Saturn's rings do. They stand vertically. From our vantage point, somewhere near the inner solar system looking out at Uranus, from a distance of several billion kilometers, the rings appear not as a flat disk around a ball, but as concentric perpendicular circles around it, a target painted around a wounded world. The image carries a quiet, accidental weight, because no one painted it. Whatever struck the planet 4 billion years ago tipped the rings with it, and they have stayed that way ever since, the cosmic signature of an ancient injury rendered in patient orbital mechanics. The moons follow, 29 of them, at last count, after El-Mutamid's discovery added S2025U1 to the roster in February of 2025. Most of the 29 are small bodies a few kilometres to a few tens of kilometres across, in orbits ranging from very close to the planet tucked among the rings to very far on wide loops that take hundreds of Earth days to complete. 5 of the moons are large. They are the major moons. From innermost to outermost they are Miranda, Ariel, Umbriel, Titania, and Oberon. Their diameters are respectively 471 kilometres, 1158, 1169, 1578, and 1523. They're all roughly half rock and half ice. Their surfaces are heavily cratered, weathered by radiation, marked here and there by ridges and grooves and the scars of slow geological history. Each of them is its own small world. Each has been imaged from various distances over the years, most clearly by Voyager 2 in its single brief flyby, and each carries its own catalogue of mysteries. The strangest of them, easily, is Miranda. It is the innermost of the major moons, the smallest of the major 5, and the most tortured-looking. Voyager's images of Miranda revealed a surface that planetary scientists, when they first looked at the pictures, described in tones of frank disbelief. There were 3 enormous oval to trapezoidal terrains called coronae, Inverness, Arden and Elsinore, bounded by complex sets of parallel ridges and grooves, plunked down into older, cratered, ordinary-looking terrain almost at random. There were cliffs and scarps that defied any tidy local geology. There were what looked like attempts by Miranda to reorganize itself, decades or millennia at a time, with no clean story of how it could have done so. Various explanations were proposed, the leading current one, that Miranda is a body that suffered, at some point in its history, episodes of internal tidal heating violent enough to drive large-scale convection in its interior, with the surface features as the visible signature of those convective events, is now broadly accepted, but the details remain contested. The single most arresting feature on Miranda is a cliff, or, more accurately, a scarp, a long vertical face on the surface that drops, at its highest point, by an estimated 5 to 20 kilometres, with most modern estimates centering on around 20 kilometres, or about 12 miles, of relief. The feature is called Verona Rupes. It is, as far as we currently know, the tallest cliff anywhere in the solar system. The tallest mountain on Earth, Everest, has an elevation of around 8.8 kilometres from sea level. Verona Rupes, taking the high estimate, is more than twice as tall as a single sheer drop. It is hard to overstate how strange that is to picture. But Miranda is also small. Its radius is only 235 kilometres. Its mass is correspondingly tiny. Its surface gravity is about 0.079 metres per second squared, less than 1% of Earth's, which means that the experience of standing at the top of Verona Rupes and then stepping off would be unlike anything human imagination is used to. I want to take you, just for a moment, through that step. Stand at the edge of Verona Rupes. The cliff face drops 12 miles or so beneath your feet into a shadowed plain. There is no air. There is no sound. The stars overhead are sharper than any sky on Earth. Miranda has no atmosphere to scatter the light. Uranus, depending on which face of Miranda you're on at the moment, looms above you as a pale blue-green crescent or full disk, 4 times the angular size of the full moon as seen from Earth, lit dimly by a faraway sun. The light is the colour of deep twilight. The cold is total. Step off the edge. You do not plummet. You drift. Miranda's gravity is so faint that the initial moments of the fall feel almost like floating. The horizon barely shifts. The stars do not move. The ground inches closer in a way that takes seconds to register, then accelerates, but never to anything our intuition would call fast. Earth gravity at the surface is 9.8 meters per second squared. Miranda's is 124 times smaller. A fall that on Earth would take a few seconds takes minutes on Miranda. There is no air resistance to terminal velocity you out. There is no terminal velocity. You simply accelerate gently for a long time. A minute passes, then 2, then 5. The bottom of the cliff face is finally beginning to rise toward you in a way that suggests it is actually closer than it was. 6 minutes, 8, 10, 11. The bottom is suddenly there. The impact velocity, at the moment you finally meet the floor, is approximately 55 meters per second, about the speed of a fast bicycle on Earth. Not, by Earth standards, a deadly impact velocity in vacuum. With a light braking system, in principle, survivable. Practically, this is academic. The cold, the radiation, the lack of any air to breathe would all have killed you long before you reach the bottom. But the geometry of the fall itself, 11 minutes of contemplative, silent, slow descent in vacuum off the tallest cliff humanity has ever found, on a moon orbiting the coldest planet we know, is genuinely beautiful. You would have time to think, time to take in the dim sky and the rising stars, time to watch Uranus in its tipped phase above, time in the end to make peace with the fall itself. It is the kind of detail that crystallizes the entire system. A frozen literary court of moons around a sideways planet, with a cliff so tall on the smallest of them that the fall itself is a meditation. It is the kind of detail you might invent for a novel and then never use, because the universe got there first. And the same telescope that revealed the planet's polar cap and its hidden vortex is the telescope that found, in February of 2025, the 29th moon. S2025 U1, 6 miles across, orbiting at about 56,000 kilometers from the center of Uranus, between Bianca and Ophelia. It had been there in 1986 when Voyager flew past. It had been there in 1781 when Herschel first noticed Uranus from a garden in Bath. It had been there for billions of years, but it was just below the threshold of Voyager's resolution and just within reach of Webb's. We finally caught a moon that had been hiding next to its planet the whole time. Not because the moon went out of its way to hide, not because anyone was looking in the wrong place, simply because nobody had yet built an eye sharp enough to see it. That, in the end, is the lesson the small moon teaches. The universe does not require its strangeness to perform. It simply allows itself to be there and waits for us to look closely. Webb looked closely. The disguise of 27 known moons, itself almost certainly an undercount, turned into 29 and counting. And every new moon that follows will be a small, patient correction to a sentence we once thought was final. Part 13. The Standard Planet. We have, at this point in the video, walked through every layer of Uranus we can talk about. The tilt, the year, the cold, the smell, the diamond rain, the broken field, the sideways rings, the literary moons, the tall cliff. We have in essence taken a planet that for 37 years was a single bland photograph and slowly turned it back into a real world, full of strangeness, of beauty, of damage, of patient mystery. Now I want to widen the camera one more time, because there is one more piece of the picture that, in some ways, matters more than any of the others. NASA maintains a database called the Exoplanet Archive. It catalogues every confirmed planet ever discovered around any other star. By the mid-2020s, the catalogue contains more than 5,000 worlds. They have been found by a variety of techniques, most by the transit method, where a planet's passage in front of its star produces a small periodic dip in the star's brightness, and the depth of the dip tells you the planet's size relative to the star, while the period tells you its orbital distance. The Kepler Space Telescope, which operated from 2009 to 2018, found the bulk of them. The TESS spacecraft, launched in 2018, has added thousands more. Ground-based radial velocity surveys, direct imaging campaigns, micro-lensing detections, they all contribute. The catalogue grows quickly. When you look at the catalogue as a whole and plot the planets by size, the distribution does something striking. There is a peak. The single most common planet size by far is between about 1.6 Earth radii, slightly larger than Earth, and 4 Earth radii, slightly smaller than Neptune. The peak is, in a real sense, where Uranus and Neptune live. Uranus's radius is just over 4 times Earth's. Neptune's is just under 4 times Earth's. They are the closest objects in our own solar system to the dominant exoplanet size. The implication is unsettling, in a way that is hard to fully absorb on first telling. Around almost every star, the most common kind of planet is not a Jupiter. It is not an Earth. It is not even a Mars. It is something the size of Uranus and Neptune, sub-Neptunes the literature calls them, mini-Neptunes, when they sit closer to the small end of that range. Whatever the exact name, they are everywhere. They are around sun-like stars. They are around red dwarfs. They are around almost every kind of main sequence star astronomers can survey. They are, in the most literal possible sense, the standard planet of the galaxy. We have in our own solar system 2 examples of the standard planet, Uranus and Neptune. We have visited one of them once, briefly, in 1986. We have visited the other one once, briefly, in 1989. The same Voyager 2 spacecraft did both flybys. There are no other dedicated missions to either world in the data record. There are no other close-up photographs. Voyager 2 is the entirety of our intimate acquaintance with the most common type of planet anywhere we look. If you take a few seconds to absorb the proportions of that statement, it is almost difficult to believe. We have rovers crawling across Mars right now. We have spacecraft in orbit around Mercury and Venus, the closest planets to the Sun. We have flown past every major body in the outer solar system at least once, and many of them several times. We have parked spacecraft around Jupiter, the Galileo and Juno missions, and around Saturn, Cassini for 13 years, until its planned end in 2017. We have probes on the way to Europa, the most likely subsurface ocean world in our system, and to other moons besides. We have flown a probe past Pluto and into the deeper reaches of the Kuiper Belt beyond. And the most common kind of planet in the universe, the closest local examples of which sit in our own backyard, has been visited by a single spacecraft, once, in 2 brief windows of close encounter time, across 2 flybys nearly 4 decades ago. The disguise that fell off Uranus over the last few years was not just the disguise of this planet looked dull in one bad photograph. It was the broader disguise of this kind of planet is unimportant. It turns out the kind of planet we paid the least attention to is the kind the universe makes most often. The work we've been catching up on, Webb's seasonal monitoring, the cap and the vortex, the new moon, the slow rebuild of our picture of the Uranian system, is in some sense work that is teaching us not just about Uranus, but about the most common world humanity will eventually have to understand if we want to understand what is around almost every other star. We mistook the standard for the oddball. We mistook the average for the strange. We were certain, for a long time, that Earth was the normal kind of planet and that Jupiter or Saturn was the giant kind, and that things like Uranus and Neptune were the weird, small giant cousins off to the side. The exoplanet catalogue has slowly inverted that hierarchy. Sub-Neptunes are normal. Sub-Neptunes are everywhere. The unusual planet, the one whose features show up only rarely in the survey data, is Earth itself. Small, rocky, in the habitable zone, with a thick atmosphere stabilized by a giant moon. That is the exception. The rule is something more like Uranus. And the rule is wounded. The rule is sideways. The rule is rotten smelling. The rule has diamond rain falling through its interior. The rule has a magnetic field that tumbles. The rule has rings tipped on edge. The rule, in other words, is much stranger than we ever realized, and there may be billions of examples of it just in our own galaxy. Hold that. Sit with it. The thing we thought was unusual is normal. The thing we thought was normal, us, may be the unusual one. And we have visited the most common type of planet exactly twice in human history, for a total of about 12 hours of close encounter time with the same spacecraft more than 35 years ago. That is the gap between our attention and the universe's actual abundance. We have, in plain language, a lot of work to do. The wound that Uranus carries, the wound 4 billion years old, the wound that runs through its tilt, its temperature, its field, may turn out to be the wound the most common planet in the galaxy carries. We do not yet know whether the typical sub-Neptune is tipped, or frozen, or magnetically tumbled, or any of the rest of it. We will not know until we have studied many more of them. But the structural lesson is already there, in our own system, in the planet sitting at 2 billion miles away from us, quietly demonstrating what a common planet can become. The thing we ignored is the thing we will most need to understand. The thing we wrote off may be the closest, most accessible example of the planet type that, around almost every other star, is the rule. The universe set the lesson out in our own backyard. We just had to look closer. Part 14. The Return Trip. It is not enough to look from afar. This video began with a planet held still by a single photograph and a 37-year silence. It has spent the bulk of its run walking through everything that one photograph hid: the tilt, the cold, the smell, the diamond rain, the broken field, the moons, the new moon, the cliff. It has used the James Webb Space Telescope as its primary witness, because Webb is the instrument that finally pulled the disguise off. But Webb is, after everything, still a telescope. It still sits 1.5 million kilometers from Earth, more than 4 billion kilometers from Uranus. It still sees the planet only as a small disk with structure on its surface and faint rings around it, and a handful of bright points moving slowly nearby. The intimate acquaintance with a world, the kind of acquaintance that requires having an instrument actually next to it, is something Webb cannot give. For that, we will have to go back. In April of 2022, the National Academies of Sciences, Engineering and Medicine published the Planetary Science and Astrobiology Decadal Survey for the period from 2023 to 2032. The Decadal Survey is, in American planetary science, the most important document of its decade. It is a careful, exhaustive, peer-driven prioritization of every plausible mission concept that NASA might fly in the coming 10 years. It is written by hundreds of scientists across dozens of working groups. It takes years to produce. When it's published, NASA leadership reads it carefully and uses it as the primary guide to which large planetary missions to plan, fund, and ultimately fly. The 2022 Decadal Survey named, as its single highest priority flagship class mission for the next decade, a Uranus orbiter and probe, UOP for short. A flagship mission, in NASA parlance, is the most ambitious, most expensive, most scientifically capable class of planetary mission. Cassini was a flagship. Galileo was a flagship. The Mars Science Laboratory, which delivered the Curiosity rover, was a flagship. Flagships cost on the order of $2 to $4 billion. They take a decade or more to build and launch. They produce in return the kind of close-up science that no smaller mission can match. The Uranus orbiter and probe, as currently scoped, would be a Cassini-class orbiter with a Galileo-style atmospheric probe attached. The orbiter would launch in the early 2030s on a trajectory that uses a gravity assist from Jupiter to reduce the cruise time. The most favourable launch window by the current trajectory studies is around 2031 or 2032, windows when Jupiter is in the right place to give the spacecraft the boost it needs. From launch, the cruise to Uranus would take roughly 12 to 15 years, putting the spacecraft's arrival in the mid-2040s, perhaps 2044 or 2045. On arrival, the orbiter would release the atmospheric probe, which would parachute into Uranus's atmosphere and begin transmitting data on the way down. The probe is expected to survive for roughly 90 minutes before being crushed by atmospheric pressure. 90 minutes of direct atmospheric measurement is, by current planetary standards, an enormous data set. Temperature, pressure, composition, wind speeds, and chemistry profiles at every layer from the upper haze down to wherever the probe finally fails. Galileo did the analogous mission at Jupiter in 1995 and transmitted for 57 minutes before being lost. UOP's probe will, if all goes well, do for Uranus what Galileo's probe did for Jupiter. After the probe ends, the orbiter would settle into a long primary mission around Uranus, lasting at least 4 years and possibly more. It would map the chaotic multipole magnetic field directly by flying through it at many altitudes and orientations. It would image the rings at resolutions Webb cannot match. It would catalogue small moons that may still be undiscovered, including any further bodies in the size range of S2025 U1. It would watch a complete Uranian season unfold, or more precisely watch the planet across the long arc from northern summer solstice toward equinox, recording how the cap dims, how the vortex changes, how the storm activity rises across the equator as the planet's orbital geometry shifts. It would, in essence, do for Uranus what Cassini did for Saturn, provide the long, patient, intimate data set that turns a planet from a distant face into a known world. The mission is not yet funded for full development. It has been recommended by the Decadal Survey, which is necessary but not sufficient. NASA has to budget for it. Congress has to appropriate the funds. The technology has to mature, particularly the radioisotope power source the spacecraft will need. Running so far from the Sun, the orbiter cannot use solar panels and will need to be powered by the slow decay of plutonium-238, the same kind of power supply that has run Voyager, Cassini, and the Curiosity rover. Plutonium-238 is in limited supply, and other missions are competing for the available material. There are international collaboration opportunities, with the European Space Agency potentially contributing parts of the mission and certain instruments. There are open questions about exactly which launch window to target. There are still details that need to be settled, but the recommendation is in. The science case is overwhelming. The next great planetary mission, after the current generation of Mars rovers and Europa Clipper and the rest, is very likely to be a return to Uranus, the first dedicated visit in 50 years, the first close-up observations of Uranus in 50 years. Take a moment to absorb the timescales. If the mission launches in 2031 and arrives in the mid-40s, the people who first dreamed it up, the planetary scientists who wrote the Decadal Survey, who worked on the mission concept studies, who built the instrument proposals, will be in their 70s and 80s by the time the spacecraft arrives. Some of them will be retired. Some will be dead. The graduate students working on the mission today will be the senior scientists by the time the data comes in. The grandchildren of today's mission engineers will be the ones unpacking the first close-up images of Verona Rupes from a real probe in orbit, not from Voyager's brief flyby. This is generational science. This is the kind of patient, long-running, multi-decade work the universe rewards, and the kind that asks more of us than a single career can provide. But the data, when it comes, will be extraordinary. We will know how the field tumbles in detail. We will know the depth and composition of the polar cap. We will know the temperature profile of the atmosphere from a probe that flew through it. We will know whether the rings have changed since Voyager photographed them, and how much. We will know the small moons. We will know much more about the wound 4 billion years old, and whether there are aspects of it that we have not yet imagined. It will not be the end of our knowledge of Uranus. There will be future missions, eventually beyond UOP. There may be additional probes designed to fly into the rings, or land on Miranda, or sample the polar cap directly. There is, in the long arc of planetary exploration, no obvious upper limit on what we will eventually do at Uranus. What UOP will provide is the first solid foothold, the first sustained presence, the first acquaintance, and far beyond that, the lesson will continue to compound. Sub-Neptunes are everywhere. The most common planet in the galaxy is something like Uranus. The work we do here eventually will inform the way we read every transit signal, every atmospheric spectrum, every faint moving point at the edge of every distant survey image. the planet we have ignored for 40 years is, slowly, becoming the planet we will spend the next century trying to understand in our system and far beyond it. So pull back one final time and take in the whole picture. A planet rolling on its side through permanent twilight. The coldest world in our solar system, colder than anything Earth has ever been. An atmosphere that smells of rot and would suffocate and freeze you in the same breath. A bottomless ocean of crushing, scalding fluid where diamonds rain through the dark. A magnetic field knocked so far off its axis that it tumbles like a thing that is broken. A moon with a cliff so tall you would fall for 11 minutes off its edge in silence. Vertical rings standing up around all of it like a target. A literary court of 29 moons named for Shakespeare and Pope orbiting it. A wound 4 billion years old that runs through every distinctive thing about the place. And around it, the patient, slowly tightening realization that this same wounded, sideways, strange world is the closest local example of the most common kind of planet in the galaxy. For 37 years we looked at the blue marble and called it dull. We were wrong, not by a little. It was never dull. It was simply out of focus. The disguise was patient. The disguise was almost complete. And the moment a telescope sharp enough came along, the disguise fell away, and we saw what was actually there. Not a boring planet, but a wounded, hostile, magnificent one that had been hiding in plain sight at the edge of everything, while we joked about its name and looked the other way. That is maybe the deepest lesson in all of this. The thing we were most sure we understood turned out to be one of the strangest places in our solar system. The thing we ignored may be the most common thing in the universe, and the only reason we ever found out is that we finally bothered to look closer. We just had to look closer. Look more carefully. Build a better instrument. Be patient with what it returned. The universe does not always hide its strangenesses in the dark corners of deep space. Sometimes it leaves one right out in the open, painted a calm and pleasant blue, waiting patiently for us to stop laughing and pay attention. One day, hopefully not too far off, we will finally send something back, a machine built to fall into that rotten, frozen, diamond-filled dark and to tell us what is actually down there in a way no telescope can. When that machine arrives, and the first new close-up images of Uranus in 2 human generations come back across the void, we will see them in a way we have never been able to see before. We will see them after Webb. We will see them with the wound, and the rings, and the literary court, and the diamond rain, and the standard planet weight of the whole galaxy hanging behind them. We will see them with the understanding that this is the 7th planet, and it is the most patient teacher in our system, and it has been waiting all along. I have a feeling when that machine finally arrives that Uranus will have a few more secrets left. Until then, we keep looking, we keep listening, we keep doing the slow, careful work of attention. Good night, traveller. Wherever you are, sleep well.